The Earth intercepts 173,000 terawatts of solar power every single day. That staggering figure represents 10,000 times more energy than the entire human population consumes. By the end of 2024, humanity crossed an extraordinary threshold: 2 terawatts of solar capacity installed worldwide, with a record 597 gigawatts added in that year alone. The global solar industry achieved this milestone in just 2 years after reaching the first terawatt, a journey that took 68 years from the technology's inception. Sunlight behaves as a stream of tiny particles called photons, each carrying a precise packet of energy. When these photons strike a solar cell, they interact with silicon, the second most abundant element on Earth. Inside a crystalline silicon cell, atoms are bonded tightly together, with electrons locked in stable positions. The secret to liberating these electrons involves creating an electric field using 2 distinct layers of silicon. One layer, called N-type, contains extra electrons, while the other, P-type, has empty spaces where electrons could fit. Where these layers meet, electrons naturally drift across the boundary, creating a permanent electric field at what scientists call the p-n junction. When a photon with sufficient energy strikes this junction, it can knock an electron free from its atomic bond. The electric field then acts like a one-way gate, pushing the freed electron toward the N-type layer, while the empty hole it left behind migrates toward the P-type layer. Thin metal fingers at the top of the cell collect these mobile electrons, channeling them through an external circuit where they perform useful work. Here is a counterintuitive truth that challenges common assumptions about solar technology. The most efficient solar cell ever created only converts 47.6% of available sunlight to electricity. Meanwhile, most commercial panels operate at just 15 to 22% efficiency. When sunlight reflects off a panel instead of being absorbed, that energy is lost. When freed electrons fall back into holes before completing the circuit, their energy dissipates as heat. Silicon-based cells approach a theoretical efficiency ceiling around 29%. In 2024 and 2025, researchers shattered multiple efficiency records using perovskite-silicon tandem cells. Chinese manufacturer Longyi achieved 34.85% efficiency with a tandem cell, while flexible versions reached 33.6%, while retaining 91% of their performance after 5,000 bending cycles. Perovskite materials work by stacking a perovskite layer on top of traditional silicon. The upper layer captures high-energy light, while the silicon beneath absorbs lower energy wavelengths, extracting more electricity from the same sunlight. The primary barrier to commercialization has been durability, as perovskite cells historically degraded within a year compared to silicon's 25 to 30-year lifespan. Recent breakthroughs using alumina nanoparticles extended perovskite stability tenfold, maintaining high performance for over 1,500 hours under extreme heat and humidity. In the 1970s, solar panels cost approximately $76 per watt, a price that restricted their use to satellites and specialized applications. By 2010, that figure had dropped to $7.5 per watt. The decline continued relentlessly, reaching around $1 per watt for modules in 2024 and an all-time low of $2.5 per watt for complete residential installations. This 97% cost reduction over 5 decades follows a pattern called Swanson's law. Every time global solar capacity doubles, prices fall approximately 20%. Solar cells possess a remarkable characteristic that contributes to their economic appeal. Electrons are the only moving parts. They travel through the circuit and return to their original positions without wearing anything down or using anything up. This means solar cells can last for decades with minimal maintenance. For homeowners in sunny climates, payback periods now average just 5 to 7 years, after which energy becomes effectively free for the remaining 20 to 25 years of panel life. 12 photovoltaic cells can charge a cell phone. Multiple modules working together can power an entire house. As manufacturing scales up, with China adding 329 gigawatts in 2024 alone, and global capacity projected to exceed 7 terawatts by 2030, the economics will only improve further. Solar energy arrives unevenly distributed across the planet. Some regions receive abundant sunshine, while others experience prolonged cloudiness or winter darkness. The technology also faces an obvious limitation. It produces no electricity at night. Floating solar farms represent one innovative solution to the space and efficiency challenges. These installations mount panels on bodies of water like reservoirs, lakes, and even coastal areas. The floating solar market reached approximately $6.7 billion in 2024. Beyond conserving valuable land, floating installations achieve higher efficiencies because water naturally cools the panels, preventing heat-induced performance losses. They also reduce water evaporation by up to 70% and inhibit algae growth by blocking sunlight. Estimates suggest that covering tens to hundreds of thousands of square miles with panels could power the entire world using current technology. For context, the Sahara Desert alone spans over 3 million square miles. Over 685 million people worldwide still lack access to reliable electricity, with the majority living in sub-Saharan Africa and South Asia. For these communities, solar offers something remarkable: a chance to bypass conventional infrastructure entirely, much as mobile phones allowed developing nations to skip landline installation. In places like Kenya, Uganda, and Bangladesh, pay-as-you-go solar home systems have become transformative. Families pay in small installments via mobile money for systems that power, lighting, phone charging, and small appliances. These installations replace dangerous kerosene lamps and enable children to study after dark. In Bangladesh alone, solar home systems now power approximately 5.2 million homes annually, with nearly 12% of the country benefiting from this renewable transition. Solar microgrids in rural India power entire communities, enabling healthcare facilities to refrigerate vaccines and businesses to operate electric equipment. While challenges remain for places like Finland or Seattle, where sunlight is scarce, the trajectory points toward a future where clean, affordable electricity reaches billions who have never experienced it. The sun, after all, makes no distinction between wealthy nations and developing ones. It simply shines, delivering free energy to whoever captures it. As we've seen throughout this exploration, unlocking understanding, whether it's the science behind harnessing the sun's immense power or mastering a new skill, is within everyone's reach. From visualizing how solar cells convert sunlight into energy, with efficiencies constantly improving thanks to innovations like perovskite technology, to appreciating the dramatic cost reductions making clean energy accessible worldwide, we hope this journey has sparked your curiosity and empowered you to learn more. Thank you for watching. Now, if you enjoyed this breakdown, please give us a like and share in the comments. What's one unexpected topic or skill you've recently learned that surprised you?